Welcome everyone to my masterclass today, and we're going to be giving sort of introduction really to machine learning. So this is, I guess, an amalgamation of things I've talked about in the past. So I'm going to give a very introductory, I guess, practical session into machine learning, and then I'm also going to talk about a slightly more involved example where we actually picked up an output from one of the last hackathons. So Project Hack 6 is one of the challenges with Baker Hughes, similar to the challenge this time actually, and I'll show you what Oakland group did with it, and I'll show you actually what Projecting Success did with it as we picked it up and ran with the solution. So again, it's exactly what the hack should be doing. This kind of output is it's a showcase for all the good things that the hack could be doing. And if you saw one of my presentations recently, it's going to be a little bit of a repetition at the end if you saw the practical session. So if you were in that, please bear with me, because it will be some similar material. So there's a tiny URL there that you want to grab a copy of my deck. So this is going to be really useful for you. So if you just, probably the easiest way is if you just search for tinyurl.com, and then you go to tinyurl's website and then you paste in that code. So it's Y2Q3PHVG, and if somebody would kindly paste that in the chat for me, then that would be really useful. So someone, maybe one of our apprentices, just paste it in the chat, and then you should get an exact copy of the deck I'm using. So this deck is actually sat in GitHub at the moment, and when you hit that URL, you'll just get a copy of it downloaded, and then you can follow along. And there are a few links that you're going to need. So has everybody got a copy of that deck? If you haven't, then please speak now. Come off mute, just say you're having a problem. It's going to be very useful.
Katie's posted it in chat, James.
That's brilliant. Thank you for that, Katie. Okay, I'll push on. So it sounds like the link is in the chat. So everybody just click that and you'll get a copy of the slides and just follow along with me. So some accounts you're going to need. You're going to need a Google account for this. We're going to do a lot of this coding together in Google Colab. So I guess everybody has a Google account, right? If you don't, then you've got about 5 minutes to go to that sign-in link and make yourself a Google account. But I'm sure everybody on this call will already have one. So that's all you're going to need. So in theory, that's us completely set up now. We just need this deck and Google Colab and a Google account. That's all we need. So we should be completely fine. So I'm just going to give an overview of who I am, maybe why you would choose to use an IDE, and maybe which one you would use. I'm going to talk about how to make progress on your own, a bit of a justification for maybe why you want to use Python. We're going to talk about what machine learning is, and then finally we're going to look at some examples at the end. So my name's James Smith. I have a background in mathematics. So I have a PhD in applied mathematics, which I completed 5 years ago now. I spent a couple of years lecturing at the University of Kent, and then I joined Projecting Success in 2017. And I'm really interested in machine learning, Python, and obviously maths as well. So you might have heard people talk about IDEs, and you don't really know what they are. So IDE stands for Integrated Development Environment. And it's basically a piece of software that allows you to code in a more efficient, easy, I guess, more structured way. So the screenshot I've got on screen is actually a picture of Spider, an IDE, and you have a few different others. So you have Visual Studio from Microsoft, which can handle about 32 different programming languages, maybe even more. You have Jupyter Notebooks, which again, it comes as part of Anaconda, which Spider does as well. So if you're interested in starting coding, I'd recommend downloading Anaconda, and then you get Spider and Jupyter. And Jupyter runs in the browser, although all the computation is done locally. Jupyter's a really great platform to learn because you can see all the outputs. So when you write a piece of code, you have the cell outputs below it, which is really convenient. And then Google Colab is another IDE, and that's what we're going to be using today. But that's actually connecting to Google servers where Python's actually running. It's not running locally for you, it's running in the cloud on Google servers. So they have to pay for all the computation, and they have to worry about all installing all the software. So you could do this on your phone, you could do it on your tablet, you could do it on your computer. So it's really easy. And basically, I use Spider, the one you can see at the moment, for when I'm developing a new piece of code for myself. I use Jupyter Notebooks when I'm teaching because of this cell. You can see the information that you're writing and you can see the outputs of each cell. But if I'm giving a presentation, then I use Colab because there's no setup cost for me. I don't have to worry about people installing anything and waiting ages. So it's really convenient in that respect. And the reason I'd use an IDE and not just code in the terminal is because this way I could really easily save and reload my files. So if I spent a lot of time developing a file, then I can just save it and reuse it. I can also run code from within a different environment. So I don't have to go into that current working directory within my command prompt and run it from there. It's also got debugging support. So if I do make a mistake, the IDE will give me maybe a prompt that I've got an extra space in there that I don't need, or I'm missing a bracket, and it will highlight that for me. And it's got syntax highlighting, so you can easily spot the difference between lists and variables, functions, etc., etc. So it makes your code much, much more readable. And it's also got automatic code formatting. So Python, you'll see that indenting is really useful. So in order to show Python when to say finish a loop, then the indent is actually what dictates that, and it automatically indents when you need to. So you might be thinking, I'd like to make a bit more progress on my own with Python. And there are some useful resources here, and I'm going to talk through the pros and cons of each in them. So Udemy is a really great source, and if you look on things like Hot You Go Deals, you'll find really good examples of when courses of the prices have been reduced, but ultimately haven't really got much support. So if you find that it's not particularly relevant or you get stuck, you haven't really got somebody to go and ask. And I guess GitHub is great, and there's a good community, but the learning curve can be horrendously steep. And if you think you're trying to solve something simple and you go in to look at somebody else's GitHub repo, you might get bogged down immediately in something that's quite complicated. Stack Overflow is great for troubleshooting small problems, but doesn't really give you very kind of holistic examples like Udemy might do. And there's a tremendous community. Just be careful if you post, because they can be quite angry about posts that aren't very specific. And YouTube, again, really, really holistic examples, a really great place to learn, but examples can be quite outdated because nobody really monitors that, which can be really frustrating because all of this moves at pace, and you might be jumping into a video that's 6 months old, 2 years old, 5 years old, and you replicate the code and it doesn't work. And then obviously there are more kind of structured means of learning. So we've mentioned the Project Data Academy, and we've got lots of our learners here. So if you're more interested in that, then please get in touch with us. And you obviously get the benefit of a lot of these things. So you get the support, you get the up-to-date learning, and you also get holistic examples, but you also get the sort of specific help you need through things like drop-in sessions as well. So a bit of a justification for why you might use Python. And this is some of the projections for what might happen with, so this is future traffic for languages that have been searched. And you can see that I think the data runs up to 2018 here, but the projections that Python is going to accelerate past Java, past PHP, plus C++. And that's because Python has such a low learning curve, but it's also super flexible. So you can do so many things like build websites, you can build machine learning models, you can create ETL processes, you can make games, you can basically do anything with Python. You could build a home cinema with it, you can build your own cloud storage, you could build a calculator, you can build any desktop application. It's incredibly versatile, very easy to read, very easy to get started with. So that's why really I think Python is becoming so popular in recent years. Okay, but we're not really here to sort of sing Python's praises. We're here to talk about machine learning. And what is machine learning? So it's a type of AI, artificial intelligence, that enables self-learning from data. So it's an algorithm. So a machine learning algorithm is something that can learn from maybe data and start to make decisions without being explicitly told to do anything. So we might be able to recognize patterns in data and then put explicit instructions in place, like if a new value falls in a certain range, then do this, or if a value is above this, then do this. But the whole point of machine learning is we don't have to do that interrogation and analysis. The model learns the patterns and then makes decisions on its own. And it does this using statistics and various different methodologies that help it process the data in the way that it needs to. And there are a couple of types of machine learning. So you might have heard about supervised and unsupervised machine learning. And personally, I prefer supervised machine learning. So this is where you have labeled data and you actually point the model at some training data and you train it on that labeled data. And then when you have new data come in, you've got a model where its parameters have been defined and you can classify, for example, a new piece of data. Unsupervised data is where you don't necessarily have labeled data in that way, but you just point the model at some data and you cluster it, for example. So you try and segment that data into different clusters and you don't train it in the same way. So supervised models can be things like decision trees, logistic regression, that kind of model. So there's sort of more traditional type machine learning, in my opinion. Today, we're going to be focusing on supervised methods. So there is quite a lot happening in the project space with machine learning. So there are a few companies like MPlan, Forecast, and Shark Tower, which are doing a lot with artificial intelligence and machine learning. So MPlan, their tagline is that they have the next generation of risk assurance, and they're essentially sucking in schedules from construction projects and trying to quantify the risk in those and making predictions based on that historical data. And if you want to know more about that, then Deb's given some fantastic presentations at our meetup. You can find them on YouTube. Now, Shark Tower have also presented very recently, actually. It was about a week ago or 10 days ago. And they've got a model that allows you to, I guess, forecast and allocate across projects the skills that you require. So you can quickly search colleagues and skills and see who's available and allocate that workload. And again, they gave a fascinating presentation very recently, which should be on YouTube for you to check out. So if you head to our PDA YouTube site, you should be able to find it easily. And another company, Forecast. So Forecast are trying to eliminate the need for a human in the planning and execution phases of a project. So Forecast knows your risk. It knows your resource restrictions, and it knows, and therefore it can start to plan the project out for you. Where normally this would have been the job of a PM. So it allows the PM to go and add value in other areas of the project and not get bogged down right at the beginning. So I'm going to jump straight into a machine learning example. So this is the iris data, and I'm just going to start off with this before I move on to the more interesting Baker Hughes example, just to give you a 5-minute walkthrough so that you start to understand some of the concepts we've just discussed with regards to kind of labels. We're also going to talk about features, or commonly known as attributes, and it should give you a good basis to understand what Oakland Group did at Project Hack 6. So if hopefully everybody's got the deck now, and if you go to the GitHub URL there, so it's just behind that string GitHub on the page. And if you just right click that, and you should get the GitHub URL there. So this is you just want to have that in stored in RAM, so just copy it for the time being, and then head to this colab.research.google.com webpage. So I'm going to do exactly the same thing. So I'm just going to right click this, click copy link, and then I'm going to head to that Google page. And just whilst you do that, you're going to get presented with this page. Okay, so you're going to have this kind of splash screen of with these different tabs along the top, and you just want to click on the GitHub tab. And then once you've done that, you do want to paste the link that we've taken from the deck, and then click on the magnifying glass there, and it will load my it will load the script from GitHub. So the link I've sent you, bear with me for a second. That's the link I've sent you, and it just takes you to my GitHub page, which is where I save all the resources I give for these hackathons. So it's just a script. It's actually what we call an IPython notebook that's saved in GitHub. So if I just head to Colab as well, I go to GitHub like you guys have just done. I don't want to include private repos. I paste the link in there. I click the magnifying glass, and then I wait for a few seconds. And the really nice thing about this is I've set this up.
Can we get the GitHub link? Sorry, where can we find that?
It is in the deck. Have you got the deck?
I've got the PowerPoint, yeah.
So it's in, if you just right click GitHub here and click copy link there. So let me show you.
Yeah, if you don't mind, yeah, we can't see it.
So just here, if you click GitHub there and click copy link. So it's just, this is just a hyperlink.
Right. Okay.
Is that okay? Right. Just let me close. Got these authorizations for GitHub, and they keep causing a problem. So is everybody at this stage now where they've got my GitHub repo loaded into Colab? If not, please speak now.
James, could you post that link in the chat here? I can't, even when I right click and copy, I'm not getting the full URL.
Yeah. Done. Do you see that? Make sure you copy all of that, won't you, Thomas? Because it's only made a section of that hyperlink, so you want to copy the whole thing.
Yep, got it. Thank you.
No worries. Anyone else having any problems? Okay, in which case I will I'll move on. So there's a piece of code here right at the top, and the beauty of this is I've loaded everything in here for you. So all the images, all the data is pulling them all from my GitHub. So they're all stored on GitHub on public repos, so you can access it all from Colab. So you remember the code, you've got the code sat in Google servers right now because you've imported it, but all of the data and all of the images are all sat on GitHub, and you're actually connecting to GitHub to get all of those dependencies, and then we're running the code here. So this is really, really awesome. And as soon as you run, so we want to run this first cell here, so hopefully you can see this, and it's going to say, warning, this notebook is not authored by Google, but trust me, it's fine. I wrote this code, so you have no concerns running it. Just click run anyway. It's running on Google servers anyway, so you don't have to worry about it getting in some loop and running for hours. That would be Google's problem, not yours. So we're just importing a couple of packages up here and this string, because I needed this stem URL to access different bits of data and images from GitHub itself. So I just need you to keep running these cells with me, and we're just going to talk through them. So we're just going to show an image to start off with about what this is all about. So I'm just loading this file name and then loading this image. So hopefully you should once you've loaded this third cell here, you should see this image. And this is what this piece of machine learning is all about. So we have these 3 different flowers, versicolor, setosa, and virginica. And we have what we call sepal length and petal length, and sepal width and petal width. And we've got some data on this, and given a new bit of data, we want to classify one of these, this flower as either versicolor, setosa, or virginica. That's ultimately the problem. So we load a couple of packages here, pandas and matplotlib. So pandas is for essentially for data cleaning. So this is what we're going to use to do all the manipulation of the data. And then matplotlib we're going to use for our plotting. And then we're just going to read the data in. So remember, we're reading it from GitHub. So it's coming from another source on the internet. We don't have to load anything into this manually. So let's load it in, and we've called that data iris there. And then we're just going to have a look at the headers. So you can see this is just the first 5 rows. So we've got the sepal length, the sepal width, the petal length, and the petal width. Those are our features in the data. And then our label is the species. So we're only looking at the top 5 here. So we've only got the iris setosas. And if we just load the next piece of code, then you can see exactly what the sepal length and sepal width is, and the petal length and petal width. So those are the measurements. So somebody's literally gone out with a tape measure or a ruler and measured hundreds and hundreds and hundreds of these in order to build this training set so that we could classify new entries. So just loading the next image. So just to clarify, this is what we really want. So we want to build a model that takes in the sepal length, sepal width, petal length, and petal width into the model. And then out the back of that, we get a prediction of what species it will be. And we're going to create that model by training it on some training data. So now we're going to do a bit of exploration. So you can see I'm just using group by here, grouping by species, and just printing the mean. So you can see we've got the means of 3 different species, and then we've got the sepal length, the sepal width, the petal length, and the petal width. And from this, we can see how predictive the data is already. So if you gave me a new flower with a low petal width, so this one in the top right-hand corner of the table, you can see this would almost certainly be a setosa. Okay, if it was 0.2, for example, it's probably not going to be one of the other species. And the same, say that we had a very, very low petal length, say it was about 1.5, then we would it's probably not going to be versicolor. It's probably not going to be virginica. It's probably going to be setosa. Okay, so now we're going to step towards some of the modeling. And Python doesn't really work very well with these species being words, being strings. Okay, so we're just going to convert them to an index. So we're going to convert setosa to 0, versicolor to 1, and virginica to 2. So that's all that does. Okay, and then the piece of code below that, it just creates lists for us. So we want to make some plots here. So we're going to get them out of tables into some lists. So we just got 4 different lists and then an extra list for the species. So just a list for each of those different features. And then we're just going to make our first plot. So here we're going to plot the sepal length against the sepal width. And you can see the colors there represent the species. So you've got the purple is setosa, the green is versicolor, and the yellow is virginica. And you can see automatically there's quite a nice separation between the setosa and the other 2. So there's already a lot of predictive nature in the data that we can see in just 2 dimensions, and we've got 4 dimensions. Again, if we plot the petal length against the petal width, then again this is perfect for a classification problem, because we could see if we added a new dot to this graph, we could probably say with a pretty high level of accuracy what species it would be. And again, we're just looking at 2 dimensions here. When we actually build the model, we're going to look in 4 different dimensions. So the next piece of code, we're going to take a model from Scikit Learn, and we're going to take what we call the test train split. I'll explain more about that later. We're going to take the shuffle, and we're going to take the logistic regression model, which is a very, very well studied classification model. And for the purposes of this demonstration, you don't really need to know too much more than that. After that, we're going to shuffle the data. So if you imagine we've got 100 rows of data, but the last 10 were collected by somebody who was having a bad day. Let's say they'd been to the pub the night before and their measuring was a little bit off. We wouldn't want to train on the really good bit of data and then test on the bit that's been collected by somebody with a headache, because the results would be not very accurate. So what we do is we shuffle the data. So if we have got any strange results, or maybe it was a particularly bad year or a particularly bad day or whatever it might be, just to make sure that data is all completely shuffled and more uniform. And then we just have a look at the headers. So you can see the index on the left now doesn't start from 0, 1, 2, 3, 4. It's been shuffled, so it's all over the place. And we just have a look at the headers. Again, the index is the same as it is in the features, but we've only got the labels here. So just remember, features are what you train your model on, and the label is what we're trying to predict. So now we use what we call the test train split, and we've actually used a test size here of 0.2. So that means 20% of the data is for testing, 80% of the data is for training. So that's what you do with a supervised machine learning model. You take 80% of the data and you train your model, and you get your model as accurate as you can. And then you say, how accurate is this? So you point the model at the 20% and you say, because you've got labels in there, so I can make a prediction, and then I can compare it with the labels I've got and say, actually, you know what, this is 99% accurate, for example. So we've only got 150 rows of data. So we're using 120 to train, and then we're going to use 30 to test. So this is extremely low amount of data, and you can see how accurate this can be with just a small amount of data, because the data is so predictive. And here we're just showing the features train head and the labels train head in a table. And then we're just going to define our model. So this is going to be this classification model using logistic regression. And then we're actually going to fit it. So this can just take a few seconds to fit it. So we're saying fit the model to my features train and my labels train. So we're fitting it on all the features based on what the labels are at that point. And now, now we've actually got that model. That's called saved as a variable called my model. We can make some predictions. So we make those predictions and we print them out in a list. So that's what the predicted species is going to be for those 30 flowers. And then below that, you can see the actual values we printed. So mine is pretty accurate. It looks like about maybe the 12th one is wrong, and maybe about the 18th one is wrong as well. But other than that, it looks pretty good. And then obviously we can just calculate the percentage accuracy. So my model here was 93% accurate. And that's because it's just worked out what percentage of those 30 it's got right, and which ones has actually got wrong. Does anyone have any questions for me about that?
A quick one. So I ran it as well and got that the score is 0.9. So is there a bit of kind of randomness in it?
So the reason that you'll get a slightly different score is nothing to do with the logistic regression model. It's to do with the shuffle. So when you make a shuffle, your shuffle will actually be different to mine. So you'll actually be training your model on a slightly different data set to me and probably everybody else in the room as well. And then equally, you'll also be testing your model on a slightly different data set. So that's why the results will be slightly different.
Okay, cool. So if you did run it again on exactly the same training and test data sets, you'd get the same score?
Yes.
Okay, thanks.
But if you ran the whole script again, the shuffle in Python is as random as it can be. So it will be a different shuffle, and you will probably get a different result. Did anybody get 100% in here?
I did.
Nice. Yeah, I guess well done. No, that's great. So what I'm actually going to do is I'm going to jump back to my slides. Does everybody find at least getting to that page and following along quite easy?
Yeah, it was good.
Brilliant. Okay, so I'm going to take it up a notch. I just wanted to do that to give you a bit of a sort of a machine learning foundation. You want to understand the principles. I'm going to give you a bit of background into what we tried to achieve with Baker Hughes about 4 months ago at the last hackathon. So Baker Hughes provided us a massive amount of schedule data coming from their Primavera P6 software. And what they wanted to understand was what caused the variation in some of the timings for their activities. So all the data they had comes from this subsea production system projects that they've got. And their activity durations are all baselined, but their variance versus actual durations is what they'd like to assess and potentially minimize it. So it came from 111 schedules. There was almost 100,000 activities. It had data on incomplete and complete activities as well, which we had to filter on because we weren't interested in incomplete ones at that time. And we had features like department type, activity type, plan duration, forecasted duration, and other scheduling data as well. So I'm going to walk you through what Oakland Group did, and then what we also did to improve on their results a little bit as well. So there were 8 different stages of the solution, and I'm going to walk you through in detail what those 8 stages were. So started off by trying to sort of identify the problem using business knowledge and use cases to really ingest the problem and try and solve it as accurately as we can. Then we collected this data from P6, we cleaned it, we did a bit of exploration to see where the predictive nature was in the data and if we needed to actually do any more data preparation in the form of feature creation. And if you don't know what feature creation is, we were quite fortunate with the iris example in that the 4 features we had, so all those lengths and widths, were predictive enough to build a pretty good model. But that's very, very rarely the case, to be honest, in machine learning. And the exciting bit of I guess the data preparation is you need to get to really think creatively about what features you're going to create to give the model a bit more predictive nature. And the example I always give is if we were building a model today to predict house prices, and the only feature we had in our data set was postcode. And let's assume postcodes are unique. They're not quite unique. So all we have is postcode, and you think, okay, I'm going to train the model on the postcode, and then given a new postcode, there's a really, really good chance that postcode won't be in the data at all. It won't exist in the data set. So the model's got no hope of predicting how much that house should be, because that's an unseen record. It's an unseen postcode. Now, what we could do is we could take the first 2 characters from that postcode. So it would give you the kind of regional information. Then we could create a new column and we call it postcode region. And then we train it on that as opposed to the postcode. And then given a new postcode, we just take off the first 2 characters and then we apply that to the model. And then that would give us a more accurate way of predicting that house valuation. So that's the really exciting bit. And that's what we had to do quite a lot of. That's what we have to do quite a lot of in machine learning, because we're not always fortunate to have really great data like that iris example. Then we modeled it. They actually used a decision tree in the hackathon, and we improved that a bit. So we use an ensemble of decision trees, so lots of decision trees connected together, called gradient boost. And then we've evaluated that model to see how accurate it is. This is still ongoing, so it's not perfect, but I'll show you guys where we are. And then we're also working on the best method of deployment at the moment. And that obviously doesn't necessarily just depend on the best solution, because it's got to integrate well with the client as well. It's got to fit in with Baker Hughes' current infrastructure. So that can be quite challenging. So the problem statement, and I'll just read this out to you guys, is as a business, we would like you to help us understand our activity duration variance. Can we apply machine learning to our schedule data to understand the features or conditions that are the biggest causes of duration variance in the project? And the nice thing about machine learning is that you can do what we call feature importance. So once you've done the modeling, you can re-engineer or reverse engineer that model and say, don't just tell me what the prediction is, tell me what's making that, what's really influencing that prediction. And we'll talk about that at the end of the demonstration. And here's an extract from their P6 data, and this was just extracted into CSV files, which we can load in. We clean the data using pandas. So just as we did with Iris, where we did a bit of data manipulation using pandas, we're going to do that exactly the same way, but again in Colab. And the data explanation, which I've ignored here. So where we try to identify how predictive the data is and what features we really need to create, a lot of that was done in Power BI, just because Power BI's, I guess, ability to build sort of insightful visualizations at this level is just slightly better than, I guess, Matplotlib. And then all the data preparation, all the modeling and the valuation was all done again in Python. And then the deployment. So the deployment is, like I said, is taking it from somebody's machine where you're training it all locally and putting it into production so that the model comes straight out of their Access database. Every time the data is trained, the model is retrained, and then fresh data is passed seamlessly to the model, is classified, and then is passed back into and written back into Access. At the moment, we're working towards using Azure Machine Learning to do this, but again, trying to integrate it with Baker Hughes infrastructure. So, let's jump straight into this GitHub example. So just do exactly the same thing we did before. So hopefully this should be easy now. So just take the GitHub URL. So click copy link. I will drop it in the chat for you guys just to avoid any problems. Oh, I see some messages there. Is it worth me having a read of those? When I open Colab to sign in, then it took me to sign in.
Yeah, sorry, it was me, James. I missed how to actually get into the Colab bit with the GitHub piece, but it didn't really matter. I was quite happy following what you were doing. I didn't want to hold things up.
Oh, sorry, Mark.
No, that's fine. It's fine. So yeah, it's just where you actually go in Colab to paste it in.
Can you see this part of the screen?
Yep.
So you just go to GitHub here, this tab in the ribbon, and then you just paste it in there and click the search icon.
But I can't. How do you get that actual orange window up? The first window up from the Colab URL.
If you it should just automatically pop up. If not, then you might have to go File, New.
Oh, okay. Okay.
Does that help?
Yep, I'll work it out. Don't hold things up for me. It's all right. Carry on.
And even if you can't work it out, Mark, following
I can just
this should be absolutely fine.
Absolutely, I'm happy following.
So this is exactly the same thing. Again, this is real Python code running on Google servers. Again, all the code, all the images, all the data is being pulled from my GitHub. So just loading a couple of tools at the top. It's going to give you this warning again. Again, this is completely safe. My Python code coming from my GitHub. As long as you trust me, then it will all be fine. So this is much more complicated, okay? The Iris is where everybody starts in their machine learning journey. And then we're skipping forward a few years. So please.
James, sorry, how did you get the orange window back up again from the previous?
I would, if I were you, I'd just open a new tab.
Yeah.
Write Colab.
Okay.
And just open a new tab, and then it will just pop up for you like that.
Thanks.
You can just leave the other one there. Or just left the other one there. Right. This, like I said, this is significantly more difficult. So bear with me. We've jumped forward a few years here in complexity. So we're importing a few packages. We're going to be using pandas and NumPy, which are popular packages for manipulating tables. Again, Matplotlib, and we're also going to use datetime as well to give us access to some useful functions for creating dates and times. And then we're just going to import the data. There's actually 2 files to import here. And then we're just going to make a quick merge. So we're using pandas to merge them together. So we've got a unified data set. And then we're just using the shuffle functionality to shuffle all that information. So just as we did before with the Iris, to make sure all those drunk people measuring the flowers, all that data is all shuffled in. We just do exactly the same thing and we call that data. And then we just need to convert some of these data columns to date time. And this can take a minute. So it doesn't, when it's pulled them in, it just thinks they're strings. And in Python, you get different data types. So you get strings, you get integers, you get dates, you get loads of different data types. And we don't want it to think they're strings. We want it to think they're date times. So we're just overwriting those columns with a change in data type. And this can take a little while. Like I said, there's 100,000 rows in this data. So before we had 150 rows, now we're working with more like 100,000. And then we're just going to print some of the data types. So we're just looking at the data type of activity type number, project line number, department number, activity. Okay, and it's printing them out as integers. But this is where the data has been anonymized. So, well, I guess these are all numbers in this case. So it's saying they're all integers, but if we model it, we don't want to model them as integers because it makes more sense for a project number isn't a number in the traditional sense. It's more like a word, isn't it? You can have project name in there. So we're going to force them to be strings. So on the next cell, we say, I don't want them to be integers. I want them to all to be strings. And then we're just going to have a printout of the activity status. So that we're looking at the top 5 rows there, and then the bottom 5 rows. You see that we've got completed and in progress, completed and in progress all over the place. And if we're going to model this data, we don't care about the stuff that is in progress. We only want to filter on the complete. So I'm just going to we're going to drop all the rows that say in progress, and we're just going to focus on complete. But then if we've just got one column there full of completed, that's not going to provide any predictive nature at all. So we can just drop that activity status column. So it's now gone. And then what we're going to do here is we're just going to do a bit of feature engineering. So we're actually just going to create a new column here called the baseline start month and the forecast start month. And we're just taking the month out of those 2 different dates and creating new columns. So just like I said with the postcodes, taking the first 2, that might be more predictive than the original postcode, whereas the month here is actually more predictive than just that date, because I guess the date is far too specific. And then I'm just going to load an image for you to look at, because the activity structure is actually formed as a hierarchy, and that's really important. So when we process this, and this is why some of these machine learning projects are completely different and you can't use an out-of-the-box model. I'm just going to show you an example of this. I say it's a hierarchy, and this is how the activities are. So we've got activity 3.3.2.1.2, and we had to model this in a really, really clever way. So one of our apprentices actually wrote this piece of code, and I'm sure he doesn't mind me sharing it. It was super impressive to split this up into different features for us, because we wouldn't want to model this. We need to do feature creation on it. So actually splits up the hierarchy as whenever you jump into a bit of the hierarchy, it always contains the bit of the hierarchy before it. And if you don't know what I mean, it's probably best to run the next bit of code and look at the example. So the first stage in the hierarchy just contains the first stage. The second stage in that activity hierarchy contains that stage and the stage before it. The third stage contains that stage and the stage before it and the stage before it. And then that's what we model. So again, it took a lot of time to create that, I guess, that logic, and we had to prove that that was more predictive than other types of feature creation. And like I said, that piece of code there, although it's quite concise, it's quite complicated, and that was created by one of our learners. So incredibly impressive that they managed to do that. Dummy variables. So when we want to model what we call categorical information. So let's assume we had RAG ratings in a project. We had green, amber, and red. If we wanted to build that into our model, we would have to create dummy variables, because we can only plot things that are numerical values, and we can't plot green because it's a string. So what we do is we create 3 different columns, one called green, one called amber, and one called red. And then we have a 0 or a 1 in that column if that particular row was either green, amber, or red at that point. You actually only need to create n-1 columns, but that's just that's besides the point. Just imagine that you create 3 columns, 1 green, 1 amber, and 1 red, and you put a 1 or a 0, and then that's what we plot. So we call them dummy variables because they're not proper variables. They do extend the amount of headers we have, but they're not like traditional features. So we need to create dummy variables. Again, it's quite a long piece of code to do that, and that actually just creates separate series for us. So they're not actually in the data yet. It's just created separate columns for us or actually separate tables of dummies, and we need to put that all together. So we just use pandas here, pd concat. That's pandas.concatenate. Concatenates all those different dummy variables that we've just created into dummy tables and the original data. Then we prepare the data. So what we're going to do is we're going to split into features and targets. So remember Iris, we had all the features, so the lengths and widths, and we had the labels, which were the species. Here we do exactly the same thing. So we say x underscore data is everything but the forecast duration, and then y underscore data is only the forecast duration. So if you imagine this as an equation, your independent variables are everything but the forecast duration, and your dependent variable, your y, is just your forecast duration. And then it's really important to rescale to what we call normalize when doing machine learning, because if you were plotting one variable against another, and one was say price, and one was normalized between 0 and 1, then the one that price would have a much higher weighting, and that wouldn't be a sensible way to model it. So what we do is we divide all the values by the highest value that we see. So the highest value becomes 1, and the lowest possible value becomes 0. And then we actually split the data. So we split it into our test train splits, and we split it again 80-20. So just think of Iris. We're just creating those 4 different sets of data for us. And then we used gradient boost. So like I said, this ensemble of decision trees. That's what we're actually going to use to model this. And this can take a little while. So we're actually fitting the model at this stage. And then it's going to print done when it's finished. So I think if you run this locally on my machine, it takes about a minute and a half to train it, but I have quite a powerful i7 processor. Obviously, we're using Google's computation, so there's some machine whirring away, probably in the States or something, training all these models. Google probably wondering why we're all sat here training the same model, but they don't give you access to the fastest processors, but it's not too bad. So I think it takes about 4.5 minutes. So it's a good test to me to see if I can just fill space for a while. The nice thing about Colab is that they actually give you access to GPUs. So some other alternatives to this, like Microsoft's, they have what they call Azure notebooks, and they don't give you as fast a processor as Google do, and they don't give you GPU access. So if you've ever heard of deep learning models, then they use graphics cards to train the models, because those graphics cards are really optimized for what we call vector calculations. And they make the training of the model much quicker. But this is all when we do kind of classical machine learning, as I call it. So a model like this, then we just use your CPU. Is anybody having any problems so far they want me to go through? Is anybody struggling to get to this stage? Anybody want to ask me anything? Silence.
So I have a question, James.
Go on.
The question is whether machine learning is the best solution for this particular problem.
I think that's a really good question, because I don't think Baker Hughes necessarily wanted a machine learning problem. They wanted to understand what activities were causing problems, not necessarily the output. So I think machine learning actually goes too far, and then we need to pull it back and say, so like I said at the beginning, we can do feature importance on this and say which features really contribute to the activity variance, activity duration variance. So I think that is a really relevant point, James. This could have been solved with more conventional methods. So I think we probably could have built quite a nice report, say in Power BI, and then use something like the key influencers visual, which actually looks at the features that affect a particular label in a certain way. So I think, yeah, is that what you'd picked up on, James?
Yes, that's right. Yes, I'm just aware there's a range of techniques that can be applied under the banner of applied AI, and that machine learning is just one of them. So thank you.
Yeah, no, I think that is a really good point. And I think people at hackathons always have to be kind of aware of what I think it always comes back to trying to solve the business case, the use case, and not just throwing something really cool at a problem just for the sake of it because it's fun. In this case, I think the saving grace is the fact that we can reverse engineer the model and say what's actually influencing it. And if we didn't do that, I don't think we'd be fully solving the problem. So it's certainly, yeah, no, I think that's definitely worth mentioning. Has anyone's model finished training yet?
Hi, James. Hello. Can you hear me now?
I can,
Hello?
yes.
Yeah. Hi. My question is, what we are trying to do here, basically we try to find the reasons for example, if delaying, and on the basis of the duration of certain months. So we can find out which month, which activities normally have variances in a plan versus actual. Am I right?
So we're trying to find out what affects the length of the project. So they've got a planned and actual of when the project's going to end, and we can calculate how, from all the completed projects, how wrong their estimations were. And then we've got lots of features like all the activities. We've got things like the project manager and other features in there that describe the project. And we can say, based on all of those things, which of them are actually affecting, which of them are causing that delay. That's what we're trying to do.
Yeah, my question is, if I could do similar kind of thing by using pivot table, so like, because it's all about the sorting on, activities. Okay, so if I have a variables defined, and I can sort it out, okay, in which month, mostly which activities, so I can just sort everything. So
what you might struggle with though, and I agree with you, say that you calculated the biggest variance and then sorted them. What you might struggle with is looking at, if you've got 100 different features there, you might struggle to see the correlations between those features that are actually causing that delay. Machine learning does that for you. So it might not be, if you could identify one feature in the data that's always causing the delay, or 2 or 3, maybe you'd be able to do that. But machine learning is really, really good at looking across hundreds of thousands of features and saying, in this case, it's these 3, but in this case, it's those 5. So that's where machine learning really, really makes a big difference to this kind of problem.
Yeah, that's fine.
Right. So my model's finally trained. Hopefully yours has as well. And then we can actually evaluate it. So we haven't evaluated it here in the conventional way because it's not as easy as when you've got classification models, it's quite easy to say with the iris data that the species was either right or wrong. So we've done it in a slightly different way here using what we call the coefficient of determination. So we call this R squared. So R squared is a measure that if R squared was 0.5, then we'd say approximately half of the observed variation can be explained by the model's inputs. And the closer we are to 0, the worse the model has been fitted. And the closer we are to 1, the better the model has been fitted. So if I calculate my R squared, it's about 0.81. So we can say with quite a high level of accuracy that the model has been fitted relatively well. And again, your scores will be quite different because of the shuffle we made right at the beginning. And then we can actually do, I keep talking about the feature importance, and I've actually ranked what the model thinks is really important into the features that the model thinks is really important to make that prediction. And the results are quite controversial, really. So it says that the plan duration, and I'm sure yours is very similar, was the most important feature in making that prediction. And that's something that we're really working on at the moment, because it doesn't, I think it's definitely open for discussion that the model shouldn't depend massively on the prediction that they make. So we're working, this is still a work in progress. And that's the area we're working on at the moment, because we're not necessarily convinced by that result. And there are some exercises at the bottom. So if you're really interested in this stuff, and I've captured your imagination today, then there are a few things that you can work on. You should be able to answer those if you've got a kind of a vague knowledge of Python, and then the code above, you can reuse bits that we've already used to answer those questions. But thank you very much for everyone for watching. I hope that was interesting and you've managed to follow along.